In our code right now, we are converting the angle to ticks, and we're sending that ticks command to the 3 pulse width modulation blocks regardless of what the Z position of the end effector will be if it goes to that angle. We want to add some code here to prevent the manipulator from going to a position if the Z position of the end effector will cause it to hit the table. In order to do this, the first thing we need to do is calculate the Z position using the equations that we found in the last video by drawing the kinematic diagram and finding the homogeneous transformation matrix. Let's call the Z position by the name of a new variable. So let's scroll up to the top and let's create a new variable, a floating point variable called Z pos for Z position. Now, after we've calculated the angles for each of the joints, but before we convert the angle to ticks or write that value of ticks to the pulse width modulation blocks, let's calculate the value of the Z position and check to see if it's greater than 0. The first term in this equation is A3 times the cosine of theta 3, which in this code we're calling angle 3, times the sine of theta 2, which in this code we're calling angle 2. The next term is minus A3 times the sine of angle 3 times the cosine of angle 2 plus the link length A2 times the sine of angle 2 plus the link length A1. Now you'll notice that several errors have been detected here. Let's clean up some of the things that we need in order to make this work. First of all, we haven't created these variables for the link lengths yet, A1, A2, and A3. We need to create those variables and also give them values. Scroll up to the top. We'll create each of these variables as floating point values. We also have to give these variables values. A1 is the distance from the surface of the board up to the axis of rotation of the second servo. Use a ruler or calipers or some other measuring device to measure that distance and type it in here. You can use whatever units you like, you just have to be consistent with yourself. When I do my measurements in inches, I get this value to be equal to 2.375 in units of inches. Link length A2 is the distance between the two axes of rotation of servos 2 and 3. I've measured that distance to be about 1.75. Link length A3 is the distance from the axis of rotation of servo 3 to the farthest point at the end of servo 3. I measured that distance to be about 1 3/8 inches. Now we've entered the link lengths, let's go back down and clear up some of the other errors that we have here. Here we have a warning, not an error, but this is something that we have to deal with. We've used the C functions cosine and sine, but the compiler of PSOC Creator is not automatically set up to be able to interpret sine and cosine. There are a couple of things you have to change. First, go to the Project menu and find Build Settings. Open up the menu Assembler and click on General. Here, there's an item called Additional Include Directories. We have to tell PSOC to use the math directories also. Type the letter M here and hit Enter. We have to do this not only for the assembler, but also for the compiler and for the linker. Click on their general items, and in Additional Include Directories, type M and hit Enter. You'll notice that the M turns bold when you hit Enter, indicating that it's been received. Do this also in the linker. And do this both in additional library directories and additional libraries. Then click OK. We also have to add a line up at the top to tell it to include the mathematics library. Mathematics functions are stored in a file called math.h, so we'll include a line that tells the compiler to include the math.h library. When we scroll down, we see that all of our warnings have disappeared. However, we've still made one error in this line of code that we have to fix. The sine and cosine functions that we've used expect to be receiving a value in radians, but we've given values in units of degrees. We need to convert all of these angles into radians before we compute the sine and cosine. We can convert to radians from degrees by multiplying by pi and dividing by 180. We need to do this for each of these angles. Multiply by pi and divide by 180. This conversion is approximate because I'm only using 5 decimal places for pi, but it's accurate enough for our purposes. Now, here's how we can use the z position that we've calculated. We only want to write the value of ticks to the PWM compare if the value of z position is acceptable. So we'll say if z position is greater than, let's give a little bit of a safety factor here, and this is in units of inches for me because I put in my A1, A2, and A3 value in inches. So let's say if the z position is greater than half an inch, in that case we'll convert the angle to ticks and write the number to the right compare. So here, if the z position is not greater than 0.5, the servo will not move because we are not converting the angle to ticks and writing the value of ticks to the PWMs. So let's test this code now. First, let's build it to check if we have any errors. If we have no errors, we'll go ahead and program the PSOC. So let's test this and see if it works. first, I'm going to hit some of my switches to make sure that it's still working the way we expect. So if I hit the direction switch and the first switch, servo 1 turns, and we can turn servo 1 back. I'm going to try and drive the end effector into the board. If our code is working correctly, I should be prevented from driving the end effector into the board. So let's drive servo 2 down a little bit, and then I'll hit the direction switch and the switch for servo 3 to tilt it down towards the board. Then I'll go back to servo 2 and try and tilt it down to hit the end effector into the board. And you see that when the end effector gets to be about 1/2 an inch above the surface of the board, let's see how well it did. Yep, that's about 1/2 an inch. It stopped and it won't let me drive it any further. Now it should be that if I hold the direction button and drive servo 2 back up, it'll take a little while, but then it'll move it back up. If I try to drive it back down again, it'll once again stop me about 1/2 inch above the board. And it should do this at any combination of angles. So if I drive servo 1 over to a new position on the workspace, and I now try to drive servo 2 down, it should still stop me. It should stop me no matter where on the workspace we are. When the end effector gets to be about 1/2 inch above the board, it will stop moving and prevent me from hitting the end effector into the board.